For any exam-related queries, call us at +1 678 648 4277. You can mail us at info@livexamhelper.com or reach us at https://www.livexamhelper.com. Problem M.1. In this problem, we will study a class of codes called product codes. Suppose that C1 and C2 are two binary linear block codes with parameters N1, K1, D1, and N2, K2, D2, respectively. We will assume that the first K1 and K2 coordinate positions are information sets of C1 and C2, respectively. The product code C is the code obtained by the following three-step encoding method. In NK, the first step, K1 independent information bits are placed in each of K2 rows, thus creating a K2 times K1 rectangular array, see Figure 1a. In the second step, the K1 information bits in each of these K2 rows are encoded into a codeword of length N1 in C1, thus creating a 2 times N1 rectangular array, see Figure 1b. In the third step, the K2 information bits in each of the N1 columns are encoded into a codeword of length N2 in C2, thus creating an 2 times N1 rectangular array, see Figure 1c. Figure 1. A. K2 times K1 information bit array. B. K2 times N1 array after row encoding. C. N2 times N1 array after column encoding. Given an N, K, binary linear block code C, show that the first K coordinate positions are an information set of C if and only if there exists a generator matrix G for C whose first K columns form a K times K identity matrix. Solution. Given an N, K, binary linear block code C, a set of K coordinates is called an information set of C if the codewords run through all 2K possible binary K tuples in that set of coordinates, i.e., if there is a unique codeword associated with every possible binary K tuple in that set of coordinates. Thus, if the first K coordinate positions are an information set, then, for 1 less than or equal to j less than or equal to k, there exists a unique codeword gj that has a 1 in the jth coordinate position, and a 0 in all of the other first K coordinate positions. The codewords gj, 1 less than or equal to j less than or equal to k, are then obviously a set of K linearly independent n-tuples, so they may be taken as a basis for the N-K linear code C, i.e., gj, 1 less than or equal to j less than or equal to k, may be taken as a set of generators for C. If the gj are taken as the rows of a K times n generator matrix G for C, then C equals UG, U, F2, K, and the first K columns of G form a K times K identity matrix, i.e., G is the desired generator matrix, which is called a systematic generator matrix. Conversely, suppose that C has a systematic generator matrix G, so C equals UG, U, F2, K, where the first K columns of G form a K times K identity matrix IK. In other words, G equals IK P, where P is some K times n minus K matrix. Then C equals UG, U, F2, K equals U, IK P, U, F2, K equals U, up, U, F2, K. Thus, as U runs through the set F2, K of all binary K tuples, the codewords of C run through all 2K possible binary K tuples in the first K coordinate positions, so the first K coordinate positions form an information set for C. Note that the encoding method given above is well defined if and only if the first K1 and K coordinate positions are information sets of C and C, respectively. 2-1 and C2, respectively. B. Show that the encoding method given above produces the same codeword whether the encoder encodes first rows and then columns, or first columns and then rows. Solution. It is obvious that for the same initial K1, K2 information bits in the array of Figure 1a, the same encoded bits are produced in the top and left quadrants of Figure 1c. Therefore, the assertion needs to be proved only for encoded bits in the lower right quadrant. Let us therefore look at a particular encoded bit in the lower right quadrant, say the encoded bit BTM in row and column M. Let G1 equals IC1P be a systematic generator matrix for C1, and let G2 equals IC2Q be a systematic generator matrix for C2. Let the information bits in the top left quadrant be denoted by Weege, 1 less than or equal to I less than or equal to K2, 1 less than or equal to J less than or equal to K1. Then an encoded bit BIM in the top right quadrant is given by. Similarly, an encoded bit in the bottom left quadrant is given by. Thus, if we encode first row-wise and then column-wise, then the encoded bit BM is formed as the linear combination. On the other hand, if we encode first column-wise and then row-wise, then the encoded bit BM is formed as the linear combination. Thus, BM is the same under either encoding method. A quicker way of showing this is to use matrix notation, including transposes. Then, writing the information array as we have Figure 2. Proof that row/column and column/row encoding produced the same result. Note that this result implies that if an n2 times n1 array is a codeword of C, then every row is a codeword of C1 and every column is a codeword of C2. C. Show that the product code C is an N1 N2, K1 K2, D1 D2 binary linear block code. Solution. The proof of B shows that every bit in a codeword is a fixed linear function of the K1 K2 information bits Weege, 1 less than or equal to I less than or equal to K2, 1 less than or equal to J less than or equal to K1 information bits U. Therefore, the sum of the two codewords IJ, 1 less than or equal to I less than or equal to K2, 1 less than or equal to J less than or equal to K1. Therefore, the sum of the two codewords corresponding to two information bit arrays is the codeword corresponding to the sum of the two given information bit arrays. Thus, C has the group property, i.e., C is linear. Obviously, C is a binary block code of length n1 n2 bits. Since each information K1 K2 tuple maps to a distinct codeword in the top left quadrant, the dimension of C must be K1 K2. Since C is linear, the minimum Hamming distance of C is the minimum non-zero Hamming weight of any codeword in C. Now, if there is any non-zero bit in a codeword of C, then there must be at least D1 non-zero bits in the same row, since every row is a codeword of C1, and in each of the greater than or equal to D1 corresponding columns, there similarly must be at least D2 non-zero bits. Therefore, any non-zero codeword has weight at least D1 D2. To show that the minimum non-zero weight is precisely D1 D2, consider a weight D1 codeword C equals CI, Euro C1 and a weight D2 codeword, tensor product, array. Then the is a codeword of C and has weight D1 D2. In other words, to construct a minimum weight codeword, write down a minimum weight codeword in C1 in the top row of the n2 times n1 array. For each column, if the top entry is a 1, then write down a minimum weight codeword in C2 which has its first bit equal to 1 in that column. If the top entry is a 0, then simply fill the column with all zeros. The resulting codeword has a weight of precisely D1 D2. D. Express the nominal coding gain gamma C, C, of the Euclidean space image S, C, of C in terms of the nominal coding gains gamma C, C1, and gamma C, C2, of the Euclidean space images S, C1, and S, C2, of C1 and C2, respectively. Express the nominal spectral efficiency ρ, C, of C in terms of the nominal spectral efficiencies ρ, C1, and ρ, C2, of C1 and C2, respectively.